Good day to everyone who's listening to this presentation. We are from Group 3. We're going to do case study number 3, which is Renewable Energy Grid Management. This will be an in-depth exploration of grid management and the impact of renewable energy on our future energy landscape. Next. Okay, these are the team members. I am Jonathan Paramtaumbolon.
I am Mufti Maji.
I am Rafif Abdul Hardin Putra.
And I am Rizkiano Niko Satrio. Okay, so for the renewable energy, a short definition and conception. The first one is renewable energy, as we know, comes from an energy source such that is both environmentally friendly and renewable for our benefit. So, focusing on our study case, it includes solar and wind as the source of our energy. This energy is produced, will then transferred into batteries and used by houses. So, moving on, why is renewable energy is important for us? The first one is renewable energy, as we know, is essential for combating our climate change. It offers a sustainable to unstable alternative to fossil fuels. And for the last one is it invests in renewable resource, creates jobs and economic growth for our benefit as well. So the problems with renewable energy for us right now is weather is not stable, it changes every moment, resulting in a volatile energy production. And not only that, solar panel only works when sunlight is accessible, otherwise it can't produce energy. So for the
So,
grid management, grid management optimize energy usage across network effectively, and then integrating renewable energy to reduce reliance on fossil fuels while we maintaining the stable energy supply. And lastly, its effective grid management supports sustainable energy for future generations. Next.
our target of market for this study case is public energy providers such as PLN or other key provider. But in Indonesia, we only have PLN. And the second one is the for people, for those who want renewable energy as their backup source of energy in case the unrenewable energy is unusable or unavailable at the moment. And the third one is the governments that might want to achieve climate goals by supporting effective renewable energy integration because, as we all know, these recent years move to achieve climate goals is very significant around the world. That same goes for Indonesia, where we need a lot of electric car around Indonesia right now.
And is a simple sketch of our management system. So we have two main source of energy, which are wind turbine and solar panel, and the total energy produced from them is going to be monitored by the control panel, and from the control panel, it will be distributed into either the battery or the city, depending on the demand. If the demand is quite high, then we might use the battery to also help supply the city. And the wind turbine and solar panel are affected by two variables, local time and the weather forecast. Because, for example, cloudy weather, the solar panel couldn't access sunlight and therefore it cannot produce any energy, while the wind turbine should be able to produce more energy since at cloudy weather it should be more windy. On the other hand, if the weather is sunny or clear, then there should be no wind into the wind turbine. But the solar panel have really good access to sunlight, and therefore it can produce an optimum amount of energy. Next.
So the demonstrations for our program, which will be explained later. First is the program starts by taking historical data of weather. In our program, we choose the data from 2023 to the recent 2025. And next, the data is then processed to compute the amount of energy produced. The data includes latitude, length, and etc. We can see it later, but this is the outline. And the third one is the produced energy that is computed before in the second step will then be stored in the batteries ready to be used according to the demands from the user. Next, this is our system code. We can open it right now. Share, wait. Ah, here it is.
Okay, so this is our code, and first thing first, as always, we import all the necessary library. Some of them we don't really know what is it because Jopar just added into the code, but I know that the ngrok and pinegrok is for the server, which is at Jopar House, because we also make a website for demonstrating this grid management system, and which we will show you later on. And then after that, we make three main functions, which are the simulate daily solar energy to calculate the daily solar energy production, and simulate daily wind energy to calculate the wind energy produced per day, and the simulate daily demand to calculate how much demand is needed in a daily basis. So the first function, which is the simulate daily solar energy, uh, first thing first, we define the panel area, which is 1.6 meter per meter square, and the efficiency of 0.9 or 90%. And then we get the temperature from meteostat, and then we calculate the radiance kilowatt hour per meter square by calculating 0.3 times temperature minus 10, and with a range of 0 and 7. Why 0 and 7? Because in an average, the radiance of the Earth is between 5 and 7. However, in nighttime, the radiance is 0, so it ranges between 0 and 7. And then we return the radiance kilowatt hour per meter square by multiplying with the panel area and the efficiency. The next function, the simulate daily wind energy. We first define the rated power and the rated speed, and then we calculate the wind speed by, we get the wind speed from the meteostat, and then we calculate the norm D, which is the wind speed divided by rated speed, and then we calculate the power fraction by calculating the norm D to the power of 3 with a range of 0 and 1. So 0 is the situation where the wind turbine is not spinning, and 1 is when the wind turbine is spinning. Also, norm D is the ratio between the wind speed and the rated speed, and rated speed is the minimum wind speed to be able to make the turbine spin. And then we return the power fraction, we return by multiplying power fraction with the rated power and 24, because 1 day is 24 hours. Next.
Okay, so for the next one, the next input will be we define the simulate daily demand, and the variable we have is the length, the average kilowatts per hour, which is we input at 30, and the amount of randomness to be 0.01 or 1%. So we define demand, and for the day in range we put the length, and moving on is the weekend. So we have the day percentage by 7 in 5 or 6. Why do we use 5 or 6? Because the day will count as 0. So 5 or 6 amount is when the day lands in Saturday or in Sunday. That counts as a weekend. And for the base one, we have the average electricity kilowatt per hour multiplied by 0.8 if it is the weekend, or if it is not the weekend, we input it as 1, because we know that in the weekend people will use electricity more often than on usual. So on the weekday factor, we input it as 1 plus number of random uniform as negative 0.2 and positive 0.2. We input the 1 plus because number random uniform cannot be amount of a negative. And for the noise, we have the number random uniform minus randomness, negative randomness, and positive randomness. Next is the daily electricity we use, or kilowatt per hour. We determine it based on the base multiplied by the weekday factor and multiplied the 1 plus the noise. As I said before, the noise cannot be negative, therefore we add one amount into it. And so for the last one is the demand append, which is we round the daily kilowatt and we put 2 amount. So final one is we can return that demand for the program to process. Okay, so moving on the next code, we apply the start time to be the date time to be the 2020 October 1st for the start, and for our data to end we input it as the 1st January of 2023, and we also put the latitude and the longitude amount to be minus 6.2 and 106.8, and also we define the battery initial and capacity to be 100 to be exact. And for the last one is we input the wind amount and the total solar use to be 3 amount. And the next code will be explained by Mufti. So go ahead for Mufti to explain it.
So basically, according from the previous code, the example in this code, we start the daytime. We start at the 2020 time, 1st of October 2020, and then ends at 1st of January 2023. This is where we used it. So basically, we use the data from here to this, and the n is this. The latitude longitude is this. This is all just for example. In the UI, you can change it later. It will be explained by Jopar later. And the battery ratio, we started from 100 in this example. Battery capacity is also 100. The number of wind turbines is 3, and the number of solar is 3. All data taken from the previous one. So if, for example, you point to a data that point to a location that doesn't have any data, like for example North Korea and India in the UI that we use, the region don't have any data available. Therefore, we use this if the data is empty, then it will print no data available for these locations. Else, we use df. Why we use df? Because it will make the UI, it will make the code much simpler and much easier, and It will also make it more, how to say it, neat, beautiful, something like that lah. So basically, we got all the data from the previous one. We got the wind speed, we got the average, temperature average. Then we copy it, and wind power, we simulate wind energy with the, yeah, the previous one, the already explained from before me. Also, this is the number of wind also from before, explained by Niko. Yeah, pretty much this code is like the continuations from before. What else? Wind power. Wind power as wind power, solar power. Next, we move to the battery simulations. How much the battery is charged based on the data that we got, based on the data that the user point. Like if you point to a specific location, you got the longitude, and how much battery will it charge from that point. This is how we use it. First, we charge battery initial, like the before charging, how much is the battery already had the capacities. Next, uh, for IDX, row in the F intervals. So basically, like for every IDX, the row is, how to say it, like filled. It's not exactly filled. But basically, and also the net energy is the calculations of total renewable minus row from demand, and the charge is charge plus net energy to zero to battery capacity. And next is the battery happen, so it will round the charge if, for example, the result is decimal. And next is the battery storage and non-renewable. The amount of non-renewable energy used will be determined by the demand minus total renewable minus battery storage. And next, the non-renewable will be plus battery storage is always less than equal to less than demand and around to non-renewable energy. So basically means that the total renewable energy and plus the battery storage is, for example, it is not enough. Like the demand is much bigger than the total renewable and battery energy. Therefore, we use the non-renewable energy. It's like a fail safe, or it's like some kind of fail safe. Yeah. And so we have the graphic here, and the graphic will be explained by Jopar. Next, we have the graph, which is made by Jopar. Jopar, the stage is
Okay.
yours.
Okay. Thank you very much, Mufti. Okay. From the graph, you can see that there's a bunch of lines. Notably, first we'll discuss the red line. The red line discusses about the battery storage. It is seen that the battery storage, it increases from the 1st of October until around the end of January, that it has some storage, but it then decreases, where then we needed to use the non-renewable that is shown by the green line, that has spikes around from April to until January. That is when we will need the non-renewable. But in around October until January, there's a spike in energy production. So we don't need any non-renewables in those span of months. While the blue line is the demand that is used by the city. We can go down. Okay, this is the code for the UI. I use Streamlit because it is easy to use. The Streamlit app needs to redefine the functions because it will be written in another file. We can go down. This is the variable and selecting of the place on the map. I use volume because it has an easy library. We can go down. Okay, this is the simulate. It is the same as previously made above. It just has some UI elements such as example as str instead of print. We can go down. This is for the tabs, and we can go to the link. We can use the link not from yes. Hold on. Okay, this is the UI. We can first select the start date and the end date, and we can also pick a location manually. Like for examples, we can select on Singapore. It doesn't have to be in Jakarta. Select Singapore, just click on it. Yes. Yeah, okay. And we can go down. And we can select the area of the solar panel, the efficiency, and the number of solar panels, and all the other attributes. We can go down again, and we can just click on the run simulation. It will send the data into the main server, which is in Colab, and it will create the charts and the summary. As we can see, it simulates the wind power and the solar power generated. We can go down, and this is the charts of when we will need non-renewable power, demand, total renewable energy, and the battery storage, which we can see that it is quite efficient on January 2023 until January 2024, which there will be a slight use of non-renewable energy on those dips. And we can go, there's another tab, we can go up. We can scroll up, and there's another tab for summary where we can see the total energy usage, total energy, renewable energy, wind energy, total demand, average charge battery, and demand covered by the renewables, and also the days that the battery is fully charged and the days that are empty, which are the days that will need the non-renewable energy. And also we have another tab for the raw data if you want to look at it for yourself, or you can download it if you want to use it for other uses. We can go back to the presentation. This is the screenshot. Okay, this is the screenshot of the program, and thank you. We're from Group 3, Computational Thinking 03, and my name is Jonathan, and I'm sorry if I have anything that is wrong that I said. Thank you very much, and be yourself and never surrender.